This is example 7.3.2. It says a comet doubles its speed as it approaches the sun, but loses half of its mass as it melts away. How does its kinetic energy compare? So we have our original formula, which we have Ke equals 1/2 mass velocity squared. And what we're going to do is we're going to see what effect it has manipulating these variables on the overall kinetic energy. So it says a comet doubles its speed. Remember, speed's another term for velocity. So instead of having v, we are now going to have 2v, and we're going to square it. Okay? But it loses half of its mass. So we have 1/2 0.5 m. 0.5 m lets me know that I lost half of my mass. So now we need to look at this overall equation. We say, okay, I need to get it back to this form right here. In order to do that, I'm going to square this out, and I would get 4v squared. Here I would still have 0.5 m. I still need this half term to make it fit, so I have to deal with that. So this can't be involved in this because I need this half term to make this equation work. So 0.5 times 4 gives me a value of 2. And so what I have is 1/2 mv squared, but I have this extra 2 factor that I don't know what to do with. And that's because the kinetic energy is actually twice as much. So if you double the speed and cut the mass in half, realize that the kinetic energy of the comet is still much greater. So a comet that's going to hit the Earth, if all things being equal, you'd rather it move much slower than necessarily affect the mass. Now the problem is that comets tend to move pretty fast no matter what, so the larger the comet would be more devastating. But overall, if you could increase the mass of it somehow, but somehow slow it down, that would make it more of a possibility that you could survive a comet impact.